Welcome to Efiwe, excellence without stress.
Hi guys, it's me again, Miss Stella, your favorite physics tutor. And today, in our journey to becoming a great physicist, in our journey into excelling without stress, to becoming a great scientist, we're going to take another interesting topic in physics, which is elasticity. It is not something new, it's not something strange, it's something that we actually use in our day-to-day life. Look at the diagram here. You can see a rubber band. So what this topic is just going to basically focus on is the working principle of a rubber band. Let me just take it that way. What happens when we apply force? Force is like, okay, when I stretch it, maybe you have a younger sister and you want to pack her air for her, how you stretch it and all of that. What happens when you apply a lot of force? What happens after a while to that elastic material? So that is what we're going to focus today in this hour class. So this is the lesson agenda. You're going to understand what Hooke's law is, elastic limits, breaking points, Young modulus, and so on and so forth. And it's going to be an interesting class. You're going to really enjoy it. So let's continue. So introduction. An elastic material regains its original shape and size after the distorting force has been removed. Yeah, I'm sure this is not something new to you. When you have your rubber band, when you have anything that is elastic, what else can I say that is elastic? Let's just focus on a rubber band, because I think that's a general material everybody should be able to know. Look at the picture, the side picture here. You can see two people holding a particular rubber band. What they are doing is actually applying force. So this material, being an elastic material, will actually regain its original shape and size after they release it, or after they stop applying force on such material. So that is why it is called an elastic material. So whatever material it is you have, that after you apply force to it, it does not break. It returns back to its original shape. It is called an elastic material. So elasticity is the ability. So don't forget that. Elasticity is different from when they say, okay, what is an elastic material? You should just know, okay, this is a material that regains its original shape and size. But elasticity is now that ability. It's just like I should say, it's the power of a substance, but let's say it's the ability of a substance to regain its original shape and size after being distorted by an external force. So that is what that's what elasticity mean. So let's proceed. So Hooke's law. Don't forget what law is. I'm sure that law is not something, when you say something is a law, it is generally accepted. It is something that, it has gone through a lot of scientific processes, observation, experiments, scientific guesses, and all. For it to become a law, this is what generally accepted. It's not a theory. If it's a theory, then it means, okay, some people are still working on it. But when it is a law, it is generally accepted. So Hooke's law, what does Hooke's law state? So Hooke's law states that provided the elastic limit of an elastic material is not exceeded, a focus is on that, an emphasis is laid on that elastic limit. There is a point. It's just like you. To get to a point, maybe, okay, there's someone that is always giving you issues, stressing you. Say, if you get to a time, you say, if I snap, you won't like me. So that is just its meaning. Hooke's law states that provided the elastic limit of an elastic material is not exceeded, the extension of the material is directly proportional to the load or applied force. So simple. It's just for instance, you have a kid, a baby, let me just say a 2-year-old and a 10-year-old, and you give each of them an elastic material and say, stretch. Definitely, the 10-year-old is expected to stretch the material because more than a 2-year-old, because actually he or she will apply more force than the baby. So that is just what Hooke's law is trying to tell us. The force you apply to an elastic material is directly proportional. When you say directly proportional, it means the more the force, the more the material will extend. But there is a condition. You shouldn't just say force is directly proportional. No, this provided is so important because there is going to be a limit whereby that elastic material will not actually do that. The force you apply will not be proportional to the extension. So like I said, Hooke's law states that provided the elastic limit of an elastic material is not exceeded. That thing is so important. Whenever you are defining, don't forget that clause, provided the elastic limit is not exceeded. Force is directly proportional to the what? To the extension. So we're going to go to our board to just derive this. Don't forget, this is the mathematical expression. Force is directly proportional to what? To extension. Let's go to our board and see. Let's clean the board. Control D. So we have what? We have that. It said provided, let's not forget that. Provided what? elastic limit is not exceeded. Let's not forget that clause. It's so important. 1, 2, 3. Don't forget. What happens? Force, right? Is directly proportional to what? To the extension. And you already know that when there's a proportionality sign and you want to change that proportionality sign to a to equal to, you're going to introduce what is called a constant. So that is what F is equals to K. So this is what? Elastic constant. This K is called the elastic constant. So K can now be equals to what? F over what? E. That's force per extension. Don't forget, your force is measured in Newton, Abby, and your extension is measured in what? Meter. So that is K. The unit of elastic constant is what? Newton per meter. So I'm sure we are good with that. So anytime you hear Hooke's law, so that is the basic formula that we got from our Hooke's law. So it says that elastic constant or stiffness, which is this K, of an elastic material is the force F required to give the unit what? Extension. So I'm sure we are good with that. So let's proceed. So elastic limit, as I've explained previously, I said this is a point whereby you start giving warning that once you exceed this point, something else is going to happen. Elastic limit is the limit of force beyond which the stretch wire does not return to its original length when the stretching force is removed. That's the point. Elastic limit is the limit of force beyond which the stretch wire does not what? Return to its original length. So just look at this picture, side picture. We have O, we have E. Abby, we have O, we have E. So this point now, the material might still be looking at, okay, this is a bit elastic, but you see after this point, the material will not return. At this point, it might still return a bit, but it will not return to the original shape. But from O to this point, yeah, it's still obeying Hooke's law. Force is actually directly proportional to extension from here to this first dot. Yes, it's still obeying Hooke's law. You see, but from here to this point is where this thing is obeyed. From here to this point is the elastic limit. At this point, after this point, what's it called? The material will not return to its what? Original. But it said the region OE from the origin to the elastic limit is called the elastic region. Yes, that's the elastic region. Distinction between the proportionality limit and elastic limit. We see that Hooke's law holds up to here. This is the proportionality limit. This is where Hooke's law, and you know what Hooke's law is now? Force is directly proportional to extension at this point. But elasticity itself, and you remember what elasticity is now, a body that what? Regains its original shape or size, holds up to where? This elastic limit. So this point is where elasticity holds up to. It regains its original. But after this elastic limit though, what's happening? Nah. We're not going to experience that awesome ability again. The ability of the material to regain its original shape or size. No, you're not going to. So please don't forget, you might be asked at what point do we obey Hooke's law? From this kind of diagram, just like from here to the proportionality limit. This point is the point where Hooke's law is obeyed. That is, F is directly proportional to the what? Extension. But elasticity is actually from here to the what? To the elastic limit. Beyond this point, that ability will be what? The elastic material will no longer have that awesome ability. So that's what this point is talking about. So let's go to the next point, the yield point. That is the point after the elastic limit. So yield point is the point beyond the elastic limit in which the elastic material has yielded all its elasticity permanently and has become plastic. So this point, when the material has gotten to this point, no elasticity again, because you know after the elastic limit it has given up, because this is the point where elasticity stops. So after that point, the yield point, the material has what? Given it up. No, I'm not more elastical. I'm now close to a rope. Are we clear with that? So that is the yield point. So let's proceed. Then we have the breaking point. Just as the name implies, after the yield point, there's that point that when you just mistakenly apply force, what happens? The rubber band cuts. I'm sure we are very familiar with issues and situations like that, where you just, let me just manage this rubber band. I know that it's already this is not more very elastic, but let me use it. Once you just try to use it, what happens? It cuts into two. So that is what is called the breaking point. So now we go to the Young's modulus. This Young's modulus is very, very important in our study of elasticity. So what is Young's modulus? Young's modulus is so simple. It's just the ratio of the stress to strain. Are we clear with that? Stress to strain. So what is stress? Stress is the ratio of force and area, while strain is the ratio of what? extension to what? To length. So let's go. He said the ratio of force to the area is called the stress or tensile stress of the material, and the unit is what? Newton per meter. Why is it Newton? Because the force is in Newton and area is in meter square. Sorry, so it shouldn't be Newton. So force is what? The ratio of force over area is what? Newton per meter square. So that is our stress. Force over area. Our force is in Newton. Our area is in meter square. So that is Newton per meter square. We wrote it that this thing area is meter square. So force. And let's go to the tensile strain. The tensile strain is defined as a ratio of extension to what? Original length. It has no unit. Since E and L are the same, don't worry, we're going to solve all of that. Strain is the measure of deformation, and stress describes the what? The distorting force. So the strain measures the deformation because extension and the length. So you are just measuring the deformation, and stress describes the what? The distorting force. So let's go to our board and quickly see. Let's try to do the two. So we talked about few quantities here. We talked about our stress, right? And we said our stress is what? Force per area B over what? Area. Don't forget the unit of your force is what? Newton. And the unit of your area is what? Meter square. So what is the unit of stress? So the unit of stress is Newton per meter square. So let's go to our strain now. Our strain is equals to what? Extension over what? Over length. And don't forget, extension is measured in meter, length is measured in meter. So two of them will cancel each other. So the unit of strain does not have any unit. So now we now go to their Young modulus. So what is Young modulus? Young modulus is the ratio of stress, Abi, over what? Strain. So that is the formula for Young modulus. So we can get a general formula. So say stress, let me write it here. Stress is equals to F over A. Strain is equals to E over L. So if we bring these two together, so we have stress, which is what? F over A, right? Divided by, that is this division, strain, which is what? E over L. So if I change this division sign to multiplication, I'm going to have F over A times what? L over E. So what is that going to give me? So that is FL over what? AA. So this is another formula to solve the what? Young modulus. So let's go back to our slides. So that's how to get our Young modulus. So work done in springs and elastic springs. So let's not forget, we know that we already said that work done is force times distance. So that's how we got this formula. So they said the work done in stretching an elastic material is stored as potential energy in the material, which can do work when the stretching force is removed and the material regains its normal length or condition. Don't forget the formula for work done. You know that work done is what? Force times distance. So this is just as if we're talking about the average work done. So if you have force and you have the distance, for elastic material, the distance is represented as the what? As the extension. So that is why we have this formula, which is 1 over 2 times F times E. And how we derive this formula, we're going to go to our board to explain it very, very quickly. So let's clear the board. So remember we said that our work done is equals to what? The force times distance. And I told you that for extension, for elasticity, our distance will be represented as what? As E. And force is going to be what? The F. Then we have what? F times E as our work done, which is actually what? Average work done is now what we're going to be solving, which is going to be 1 over 2 FE. So for the work done, we're going to be having 1 over 2 multiplied by the F multiplied by the extension. This is very important. But you know that in physics, one formula leads to another formula. Remember that our F is equals to what? KE. So putting F is equals to KE into this formula, our work done can also be written as what? 1 over 2 KE E multiplied by another E, which is now equals to what? 1 over 2 KE square. So this is the two formula for what? Work done in an elastic material. So let's go back to our slides. So, and that's how we derived our formulas. Don't worry, we're going to do a lot of examples and you're going to understand it. So, elastic potential energy. You know what potential energy is, right? Potential and kinetic energy. Potential energy is the energy possessed by a body by virtue of its state or what? Its position. So, that is what a potential energy is. A stretched or compressed string, elastic string or rubber possesses what? Potential energy, because they are potentially able to do work. This potential to do work arises from the fact that work is done in stretching or compressing the elastic material. Don't forget that. Why is work being done? Remember that work is force times distance. You know, the example we gave when we were explaining work done, we told you that if a person is using a lot of force to push a static wall, we don't believe the person has done any work because the person has not covered any form of distance. But for elastic material, a force will be applied and extension will actually happen, and that is what we call the force times the distance, and that's why work done has happened. So let's solve these examples. So looking at the first example, we have a load of 5 Newton gives an extension of 0.56 centimeter in a wire which obeys Hooke's law. You remember what Hooke's law is? Force is directly proportional to the extension. So they now ask that what is the extension caused by a load of 200 Newton? This is just like the analysis I gave. The first person, let's assume that this person was a baby, was applied a force of 5 Newton, and this one was a 10-year-old person applied a force of what? 20 Newton. So they're now asking us that what will be the extension when this person that applied a force of 20 Newton, what will be the extension of the material? So let's go to our board and solve this question. Let's write out our parameters first. So we have our F1 and our F2 first. Let's clear the board. So our F1 was 5 Newton. Our F2 was 20 Newton. So let's go to the this thing to check. Was 20 Newton. What else were we giving? Our extension, Abby. The first extension was given. The first extension, which is our E1, was equals to 0.56 what? Centimeter. So we have 3 things. Don't forget the most important formula, which is F, Abby, is equals to KE. So K can also be equals to what? Force over extension. So let's use this formula. What's our F1? So we are going to have F1 over E1 is equals to what? F2 over what? E2. So let's put in our parameters. Our first force was 5, right? Over what? 0.56. And that's going to be equals to, what's our F2, which is 20 over what's our E2? We don't know it. So let's put X. So what are we going to do? We're going to cross multiply. So this is going to be 20 times 0.56 over 5, right? So we know that 5 here 1, 5 here what? 4. So it's equals to, so what's our answer? You can use your calculator. So what's our answer? Our answer is 2.24. And don't forget, extension is unitless because extension, so that's also 2.24. That's the extension. So let's check. Let's just look at it now. When the person applied 5 Newton, a baby, the extension was 0.56. Now, when the person applied 20 Newton, what was the extension? 2.24. Have we noticed that Hooke's law was obeyed? Because Hooke's law states that F is directly proportional to extension. Big force, big extension. Small force, small extension. So let's go to the next question. So the next question says, a force of 15 Newton stretches a spring to a total length of 30 centimeter. So we don't know the initial length of this spring. They are just telling us, okay, this is a rubber band. When this person applied a force of 15 Newton, what happened? The length stretched to what? 30 centimeter. So an additional force of 10 Newton stretches the spring 5 centimeter further. So let's try to understand what we are doing here. At this point, the force was 15 Newton. The person added 10 Newton. It means the force changed from 15 to what? To 25. That is 15 plus 25. So what happened to the length then? They said stretches the spring 5 centimeters further, then the question is find the natural length of the spring. So the length was actually 30 centimeters. It later went to what? 35 what? Centimeter. So they are now asking us to find the natural length. So don't forget extension. When you say something extended, so let's go to our board first. Let's go to our board. Control D. So let's go to our board. Let's write out our parameters. That's the first thing you do when you want to solve questions. You write out your parameters. So what was the first thing we were given? So we have first force was 15 Newton, right? The second F2 was what? 25 Newton. Is that not so? Yeah, so let's write that. So we have our F1. F1 was what? 15 Newton. Our F2 was that 15. And I said they added 10, Abby, which was equals to what? 25 Newton, right? So we don't know our length. But what they told us what? Initially, Abby, extension. Don't forget, extension is, what is extension? Extension is actually L2, Abby, minus what? L1. Right? So what was the L2 for this first extension? The L2 was what? 30, right? Minus what? L1. So they now said for the E2 also. E2 is what? L2, right? Minus what? L1 for that second force. And what was that? That was 35, right? Minus what? L1. So this is what we're going to put into our formula. Don't forget our Hooke's law formula, which says that what? F is equals to KE, right? So let's put our K is equals to what? F over E. So F1 over E1 is equals to what? F2 over what? E2. I'm sure we're very clear with this. Should we clean our board? Are we clear? Yes, I guess we can clean the board so that we can write it there. So we have, I said F1 over E1 is equals to what? F2 over what? E2. So what is our F1? Our F1 was 15, right? And our E1 was 30 minus L naught, which we did not know. So, and it's also equals to F2, which was what? 25 over what? 35 minus what? L naught. Because it's the same L, each of them. You know, extension is just, okay, this was the wire before. This was the length of the wire. When they force, let me delete that because Control Z. So maybe this was the string. This was how the thing was before. This was the L naught, right? So later, when the force of what? 15 Newton was applied to it, it became this. Same thing goes to, it was like this. Then a force of what? Of 25 Newton was applied to it, right? So it became like, so that's just what, this is still the same L naught. So extension is actually the final length minus the initial length. So let's go there. So you know what we're going to do next? We're going to what? Cross multiply. So here we're going to be having 15 multiplied by 35 minus 10, right? Is equals to 25 multiplied by 30, no, not 10, sorry, L, that's L naught. L naught minus what? L naught. So we're going to do the normal multiplication. You know, this will multiply this will multiply this. So that would be like 15 multiplied by 35, right? Minus 15 L naught is equals to 25 multiplied by 30 minus 25 L naught, right? So don't forget that these two, so it's just going to be 15 multiplied by 35. Yes, then this one is going to come over here, minus 25 multiplied by 30, right? It's going to give us this one, minus 25 L naught, minus what? So when this one is coming, it's going to turn to plus 15 L naught. Yes, this number is actually bigger than this. So we're going to have a negative sign. The negative sign here is going to cancel the negative sign. And we're going to get our answer. Let's check our answer from our slide. Our answer was 22.5 centimeters. So our answer will be 22.5 centimeter. So that's the answer. So I'm sure we are clear with this. You use your calculator to multiply it out, get the right answer. You're going to have negative signs on both sides. They are going to cancel out and you will get your answer. So let's go to the next question. This question says a spring of length 25 centimeter. So let's check our parameters. A spring of length 25 centimeter is extended to 30 centimeter. A spring of length 25 centimeter. So we have the L naught, Abby, is extended to 30 centimeter by a load of 150 Newton attached to its end. What is the energy stored in the string? So we have the force, we have L1 and we have L2, right? And they're not asking for the what? Energy. So let's go to our board to solve it. Let's go to our board. Let's delete what is on the board so that we can have a clear board. So yeah, we have our force. Our force was given as 150 Newton, right? We're given our L1 to be equals to what? 25. Our L2 was 30, right? They're not asking for the what? What were we asked to solve? We worked on, I guess. We're asked to solve the what? Energy. Energy can also be the work done. Yes, we're asked to solve the energy. Yes, okay. So we're asked to solve the energy. So don't forget, energy is equals to 1/2 F what? E. Right? So we are good to go. So let's check what is going to be our extension. Don't forget what I explained to you. Extension is always the initial length minus the final length. So our extension is going to be equals to 30 minus what? 25, which is equals to 5 centimeter. So we need to convert our 5 centimeter to what? Meter. From centimeter to meter is divided by 100. So this was equals to 5, right? So that will be 5 divided by 100, which is 0.05, right? So having that, we already have our extension, we have our force. So our E will then be equals to 1/2 times 150 times 0.05. So these two, we cancel this and give us what? 75. So 75 times 0.05 is our answer. And don't forget, it's going to be in joule. Our answer from our slide is 3.75 joules. So that's going to be equal to 3.75 what? Joules. And that is the answer for the work done. So let's go to the final question, which says a copper wire was subjected to tensile stress of 7.7 times 10 raised power 7 Newton per meter square. So we're given the tensile stress. I hope we've not forgotten the formulas we had. Let's delete this. So remember that we said our stress. Remember we said our stress is equals to force over area. And we said our strain is equals to extension over what? Over length. Why the Young modulus is the ratio of what? Stress to strain. So from the formula, let's write out all what we were given one by one. So we have our stress to be 7.7 times 10 raised power 7. So stress 7.7 times 10 raised power 7. Don't forget our unit, which is Newton per meter square. Then what else were we giving? We should be giving our Young modulus. Let's check. Okay, so we're giving our Young modulus to be 1.1 times 10 raised power 11. So our Young modulus. So our Young modulus was, oh god, sorry. Let me check. Our Young modulus was 1.1 times 10 raised power 11. Our Young modulus was 1.1 times 10 raised power 11. So bringing this together, so we have our Young modulus be equals to what? Stress, Abby, over what? Over the strain. And we're asked to get our strain. So let's do that. That will be 1.1 times 10 raised power 11 is equals to our stress, which is 7.7 times 10 raised power 7 over our strain, which we are looking for. So you remember you have to cross multiply. So your strain will then be equals to what? 7.7 times 10 raised to power 7 over 1.1 times 10 raised to power 11. And if you use your calculator, you're going to get the final answer. And that is it for this topic.